Hi there. In the last video, we had a look at the difference between permutations and combinations, or arrangements and selections, knowing that we really need to focus on combinations really, but we're going to do that by looking at arrangements first because there's some good building blocks here. We're going to do it by looking at some examples. So how do we actually go about working out how many different possibilities there are when we're given a situation that requires rearranging? So example one here, I've got CAT as 3 little Scrabble tiles, for example, in the bag. And you could pull the tiles out in any order. So how many different 3-letter codes could I get? So this is a pretty common kind of problem. So what I'll do is I'll draw a little, if you like, a little tray. And you can imagine you're pulling out a letter and putting it onto the tray. So how many ways could I pull out a letter and put in the first spot? Well, there are 3 letters, so that's 3 ways. And then how many letters could I put into the second spot? Well, I've already drawn out 1, so there's only 2 left. So there's 2 ways of drawing out the second one. And then I've only got 1 tile left in my bag, so there's only 1 way of being able to work that out. Now, did you notice that every time I went between those different spots there, it was 3 and then 2 and then 1. So we've got that and if you remember from our first video, whenever we see that word and or hear that word and, it's a multiplication. So how many ways can we do this? 3 times 2 times 1, which is equal to 6. Now you could also do this using a tree, for example, and you could draw that tree out, but I think you'd find that even for something small like the letters of CAT, drawing a tree diagram would be quite unwieldy. So having this sort of way of just thinking about the combinations instead of writing out the entire sample space is really quite a time saver. So what does all this mean? It means that if I said I've got 3 letters CAT in a bag and I draw them out randomly, what's the chances of drawing out the word cat? The answer would be 1 out of 6. I hope that makes sense. Let's look at a more difficult one. That's the word chosen on slide 6 here. And same deal, 6 tiles all in a bag, pulling them out one by one. So we'll start off with our tray, and I'll just split it into 6 spots as neatly as I can. And then I'll start pulling out the tiles. So how many ways could I pull out the first letter? Well, there are 6 tiles, so there are 6 ways. How many ways could I pull out the second letter? Well, we've got 1 tile out, so there's only 5 left. Now we've only got 4 left, so that's how many can go into the next spot. And then there's 3 left, that's how many can go into the next spot. Then there's 2 left, then there's 1 left. So we end up with 6, 5, 4, 3, 2, 1. But because these are 6 and 5 and 4 and 3, it's all multiplied together. So we get 6 times 5 times 4 times 3 times 2 times 1. And look, we could do that in our heads. It's not too challenging, but I'll cheat and use a calculator. So 6 times 5 times 4 times 3 times 2 times 1 equals 720. So there are 720 ways of arranging those 6 letters when pulling them out of a bag. That wasn't too bad, but imagine doing the same thing with, say, a pack of cards where you've got 52 cards. How many ways could you place those 52 cards? You don't really want to go to your calculator and go 52 times 51 times 50 times 49 times 48. I mean, you could do it, but it's a bit tedious. And this idea of multiplying down by 1 number each time until you get to 1 is really common. So our calculators have an operation which allows us to work on that, and it's called the factorial operation. So this can be rewritten as 6 factorial. That's how you write it, 6 exclamation mark, and you say 6 factorial. So if I go back to my calculator and type in 6 and then go this button here and go exclamation mark and press return, it'll give me 720. Now from memory, this will test me. I think there's a factorial menu item as well. Could be wrong. I'm just going to have a quick look. Nah, I thought there was, but maybe there isn't. Okay, so it doesn't matter anyway. So 6 factorial is how you do it. And it's a bit of a time saver. Just moving back to the factorial notation. And so looking at the bottom left-hand corner there, I've got a few notations here. So we've got 6 factorial here, which we can just simply write as 720 from our calculator. 10 factorial and 0 factorial. Pause the video, try these out, and then come back. Okay, so 10 factorial, you can just use your calculator for again. 10 factorial like so. And you get this number, 3.6288E6. Now, I know you can't see me, but I'm just going to write that down. 3.6288E6 is what it says. What does that mean? It means that you need to move the decimal point to the right 6 times. That's what that E6 means. If it was E-6, that would mean move it to the left. So I'm going to go 1, 2, 3, 4, and now I need to add 2 more zeros to make it. So that's 3628800. Go back in threes. 3,628,800. So it doesn't take long before it starts really building up. 0 factorial. If you did it, you would have got 1. If you did it before. So there's some tricky reasons why that is, and I won't go into it. I'll just leave it to say that 0 factorial does have meaning. It does mean 1, it's not 0, and that's how you should apply it. And look, if you want to know in class, let me know and I'll explain to you why 0 factorial would equal 1. Let's have a look at a couple more examples and I'll leave the video here. This is different, this one, because I've got the 6 letters again, CHOSEN, and this time I'm not picking all 6, I'm only picking 4 letters out. So my selection tray is just 4 long. Well, how many ways can I fill the first slot? It's still 6, right? Then how many ways can I fill the second slot? It's 5. How many ways for the third? 4. And how many ways for the last? 3. So that's equal to 6 times 5 times 4 times 3. Now I can do that on my calculator. It's not that bad to do really, but I'm going somewhere with this. 6 times 5 times 4 times 3, and I get 360. Okay, so that's 360. But it'd be nice, wouldn't it, if we could use our factorial notation instead to try and solve it, especially when we've got a more complex one like the cards, like I said before. You don't normally have to lay out 5 cards, but 52 cards in a deck, but you may have to lay out 5. So it'd be nice to be able to work out that sort of calculation using factorial notation. So this is what I want you to be able to see. What am I missing to use this factorial notation? I've got 6 times 5 times 4 times 3. I'll use a different color. I'm missing the times 2 and the times 1, so that's not too bad. So what I'll do, if I did have the whole lot, that'd be 6 factorial. But I have a 2 times 1 at the end there. So what I'm going to do is I am going to divide by 2 times 1. And what's 2 times 1 as a factorial? It's 2 factorial. So I can actually take a selection or a permutation down to a certain point by then dividing it by the rest of it, I suppose is the best way to look at it. So I've got 6 factorial over 2 factorial, which I can do on my calculator nice and quickly. 6 factorial divided by 2 factorial, and I do get 360 as well. So it's very, 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 very handy, that particular one, shortcut to use. So let's have a look at a couple of calculations to finish off the video, and then you'll be right to do 10b, just a few problems from 10b. So 7 factorial divided by 5 factorial. Let's have a look at this without using a calculator. So 7 factorial is 7 times 6 times, and now I'll just put 5 times 4 times 3 times 2 times 1. But 5 times 4 times 3 times 2 times 1 is just 5 factorial. All over 5 factorial. And now I can cancel out the 5 factorials, and I get 7 times 6, which is 42, I think. 6 factorial divided by 3 factorial. Now, just wanted to point out that factorial has a higher order precedence, which means that I can't just divide 3 into 6 and get 2 factorial. It doesn't equal 2. Okay, we need to expand it out like I did the previous example. So it's 6 times 5 times 4 and then times 3 factorial over 3 factorial. The 3 factorials cancel out, and we're left with 6 times 5 times 4. And that is 6 5s are 30, so it's 120. 2 factorial divided by 0 factorial might cause you to go does not exist because you're dividing by 0, but you're not. You're dividing by 0 factorial. So please don't forget that 0 factorial is just 1. So we're effectively going 2 times 1 over 2, and that is equal to 2. So just keep that in mind. Okay, the reason why I went through some non-calculator work there is because you can be asked in the non-calculator section of the exam to do these kinds of calculations, and if you get over-reliant on your calculator, it does cause difficulties, but ultimately we want to be able to use our calculator for some of the more complex ones. So I'll finish off by just one little example and then we'll be done. So if I was playing a card game and there were 7 cards drawn, so 7 cards drawn from a deck of 52. How many ways could I get those 7 cards? And because this is in the arrangement section, we're looking at specific ways. So what's the chances that I could get an ace followed by a 2, followed by ace of hearts, 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, 6 of hearts, 7 of hearts, in that order, pulled out of the deck? What's the chances? So we'd have to work out how many possible ways I could get 7 cards, and then it'll be 1 over that. So we start off with our little tray again. I need 7 slots this time. There's 1 slot, there's 2 slots, there's 3, 4, 5, 6, 7, I think. 1, 2, 3, 4, 5, 6, 7. Yep. And so we would have, I'm going to do it in a different color so you can see it a bit better. 52 ways of putting down the first card, then 51 ways of the second card, 50, 49, 48, 47, and 46. Okay, so that would be the calculation. 52 times 51 times 50 times 49 times 48 times 47 times 46. Tedious, but you could do it on your calculator. But the solution is a little bit easier. So the number of ways would be 52 factorial. That's everything. And then I'm going to divide it by, well, the bits that I don't need, which would be 45 onwards, right? So I would go 45 factorial underneath, and that'll give me what I'm left with, which is 52 times 51 down to 46. Okay, so my calculator operation simply becomes, even though we've made it much more complicated, 52 factorial divided by 45 factorial. And I know you can't see my screen, but I'm going to write that down, 6.74274 e to the 11, which means times 10 to the power of 11. And that is our answer. So I could replace it, I suppose, by going 1, 2, 3, 4, 5. So I've got 674,274, and then 6 more zeros, 1, 2, 3, 4, 5, 6. So what's that? 674,274,000,000 ways of drawing out 7 cards from a deck in a particular order. So there you go. If I could just spend a moment just conceptualizing that in general. So in general, if I'm selecting R objects from N objects, then the number of ways would be N factorial, so 52 times 51 times 50 times 49 all the way down to 0, but then I have to divide it by the difference between the two. So it would be N minus R factorial. So having a look at the example again, N factorial, because there are 52 cards, they're the objects, so it's 52 factorial on top. But then I need to cut out from 45 onwards, and that's N minus R. 52 minus 7 is 45, and that gives us our bottom number. Okay, I'll leave the video here. You have a go at the few problems that I've got for you in 10B, and then we'll focus our attention on combinations.